So just a quick recap from last time, because it's been a week. So we looked at this model for PCF, slight extension of PCF, using what I call nested sequential procedures. Just a quick refresh, here's the grammar for them. So a procedure can be of any type. It can accept some arguments and then try to compute a value. So an expression which is trying to give a value is either undefined or it's a constant. Or this is case construct where we take one of the arguments we've received already, pass that some argument and branch on the results. And we also looked at sub-languages of PCF, and differences between expressivity between iteration, recursion, and so forth, from the perspective of these NSPs. So in this lecture, we'll have more stuff with NSPs. So first, as part of the sort of computability theory of PCF, I'll show you how you can construct an interpreter for PCF within itself. In fact, there'll be a version that interprets PCF programs as such, and a version that interprets NSPs. Come on to that soon. And so this is interesting in itself that these things exist, but they also have applications to other things, which are perhaps a bit surprising. So come on to that. And there's an interlude in the middle. I'll take just a brief glimpse, for reasons of time. I'll try and keep it short, at a sample of some of the other slightly non-obvious things you can do in PCF, surprising programming tricks that are around. And then as a final topic, I'll talk about NSPs from the perspective of observational equivalence of PCF programs, where I'm thinking of observational equivalence with respect to not just PCF itself, but larger languages than PCF. So whereas previous lecture we looked at sub-languages of PCF, today there's going to be stuff about super languages, extensions. And as we'll see, the interpreters that we cover in the first part of the talk will find an application. So that's the plan. So, okay, what do we mean by interpreters for PCF? So supposing we've got some Gödel numbering fixed on of terms of PCF or whatever languages we're talking about, or any other syntactic gadgets. Then let's say a program interpreter for a type sigma is a program H, let's say in the language we're talking about, that takes a Gödel number for something, or to be really pedantic, the numeral for corresponding to a Gödel number for something. It's worth being a little bit pedantic here because it's quite easy to get confused. And then renders that as a live object of type sigma that you can actually call on arguments of the type lower down. When I say it renders that, I mean that this thing will actually be observation equivalent to M. This is for any closed term M of type sigma. Okay. Of course, if you wanted to actually really do this in yes.
What's the definition of a Gödel number?
Oh, I just mean a Gödel number is just some way of coding up terms of a language as natural numbers.
So it's just any injection?
Any injection such that the usual syntactic operations are effective.
And like computer players.
Sorry?
Effective.
Yes.
But there's no structure necessarily.
No. It can be, we just get a natural number. We've got. So what I was about to say is, if you actually wanted to write one of these interpreters in Haskell or something, you wouldn't use Gödel numbers. You'd use an inductive type of syntax trees for PCF terms. But for theoretical purposes, we're trying to think what we can do within this minimal language.
Could you say what the hat is again?
The hat is just the numeral for. So a Gödel number is so the hat turns a mathematical natural number into the numeral for it in the programming language.
I see. So just a syntax constructor.
Mm-hmm. Yes. Yeah. So it's worth being, as I said, a little bit pedantic because we've got right. Okay. So we remarked in the first lecture that in system T there's no program interpreter. Even at type NRON, there's no program interpreter you can write within system T for all system T terms. That leads to a diagonalization. problem. But we'll see that in PCF, these things do exist, and there's one for every type sigma. An interesting bit of prehistory. So Richard Klatek's thesis from 1966 actually has a proto version of PCF, so even before Dana Scott's work. And this is the first place I know of where this construction was actually carried out. So the little anecdote here is that Dana Scott has said that the reason that he invented LCF was he didn't want to have to go to the trouble of understanding Klatek's work, which was written in a sort of not the purest way. So he sort of had an intellectual debt to Klatek, but came up with something similar. Okay, so we can do this in PCF, and what's more, if we're actually working with PCF plus bivalve, we can even achieve something slightly stronger. So in place of this observational equivalence, we can achieve that the underlying NSP for this term matches that for the term M. So we said before.
So that equivalence means that when you take the NSP.
That means the NSP of each side is equal.
Okay.
Is equal. Yeah, alpha equivalent. Okay, so we'll be seeing how to do this, but just to note straight away, there's an interesting consequence of this. So supposing we're interested in what it takes to define everything, all the functions we have at type sigma, up to whichever equivalence we're interested in. Okay, so you might, PCF itself has Y combinators of arbitrary I types, but we can see straight away from this that there's a bound, there's a upper limit to the types of the Y combinators that are needed to be able to define everything at a given type sigma. That will go up. So that is because this H here, after all, is just a finite program which will involve only finitely many uses of Y in it. So you can just take some Y tau that's powerful enough to give you all of those. And then all we do is we just feed it with a number to get something observation equivalent to this. So the higher the sigma, the higher the tau might need to be. In fact, taking tau equal to sigma is more than sufficient. So there's no single Y tau which defines everything in all of PCF at all types, but to get sort of completeness at any given type sigma, you only need these finitely many Y combinators. So that's just something we can read off straight away once we've got these interpreters. And again, there's a contrast here with system T, because even if we just look at first order functions, the higher the primitive recursives we're allowed to use, the more first order functions we can define. Something we said last time, what we said in lecture 1. Okay, so actually we'll do something a bit more than just construct this H in one piece. We'll show that how we can construct this H as a composition of two pieces. So starting from a Gödel number for M, we can first of all write a program that takes us to the NSP for M. And as I'll clarify on the next slide, an NSP for M can be represented as a first order function. And then we can write an interpreter for NSPs, which takes any NSP you like, and then renders it as a live object of type sigma that you can interact with. So notice this is doing something stronger than merely constructing H, because we're throwing away quite a lot of information and going from M to its NSP. So what this is saying is that even the NSP retains enough information to allow us to do this simulation, as it were, and produce something type sigma. So okay, so let's just clarify now how we're representing NSPs. So NSPs are trees, they're lazy trees. Again, if you wanted to do this in Haskell, you'd use some type of lazy trees that was civilized. But if we want to represent it within our simple type system, let's say an NSP is a partial function from addresses to labels. So addresses are identifiers for just positions in the tree. So they're finite paths through the syntax tree. So here, supposing we start with a procedure, the procedure only has one child, which will be an expression. And then we can say, let's take the second left branch, talked about left versus right branches. And then we go down to an expression, then take the fifth right branch, and so on. So we've got addresses identifying positions of nodes in the syntax tree, and labels are the information that that's present at that node, which might be a lambda abstraction on a certain number of variables, so a case expression with a choice of variable here, number for n. There's not going to be a label for bottom because having bottom is going to correspond to this partial function being undefined at that address. So that maybe takes care of some of the worries. So setting out things like this gives the right answer to the question, what's a computable NSP? Because we had a bit of a discussion last time about how do we know when there's bottom or something. Also gives the right answer to Sam's question last time about what's a finite NSP. So one with a finite partial function here will be reasonable. Okay, so because we can now Gödel number up these bits of information, so we can think of an NSP as a partial function from n to n. So we can represent that by thing of type n arrow n. So we've now got a clear notion of when a closed term capital P this type represents an NSP at that type. If it just represents the partial function on n that corresponds to this. Okay. So, as I say, we're going to construct these two components which compose to give an interpreter on programs. So what we claim about it, so J, remember, takes us from Gödel numbers to NSPs. So we claim we want it to be the case that for any term m, J of the numeral for the Gödel number of m represents, in this sense, the NSP for m. And the second half, for any closed NSP tall of the right sigma, if we've got a program capital P representing little p, then applying I sigma, this is this sort of an interpreter for NSPs to P, gives you something whose underlying NSP is going to be little p, the little p moving. So in particular, if we compose these, then we'll get something that's observation equivalent to the original n. Okay. Now, the first part of this is actually easy because we've kind of already done it in the last lecture. So I gave you a definition, in fact, I gave you two definitions of how you interpret a PCF term as an M and NSP. Those are, so for instance, the compositional definition by structure on M is immediately gives you just a recursive program that defines the NSP. So you can just write that as a PCF program, and that's yes.
So that doesn't depend on J's for other symbols?
This is an interesting question. You could write J sigma actually independent if you've got enough. Yeah, if you set things up with enough type information around, you can write J sigma independently of sigma. If you want.
Well, my question was, does J sigma depend on other J's for other types besides sigma? Can you write it?
No, it doesn't, because we will have that issue with I sigma, but J sigma is just going from type 0 to type 1. Everything lives at, so whatever subterms we're interpreting, the NSPs, yeah, you don't see any type distinctions at the level of either Gödel numbers or the NSPs themselves. You can do
the operation samples.
You go from untyped programs to untyped.
Yeah, you go from untyped programs to untyped NSP. You can do what you like as regards to types. But the issue you raise is a very relevant one because, as we'll see when we come to how you write I sigma, which wants to end up in type sigma, okay, we definitely do have that problem. We have to care about the types. Okay, so one's easy, so let's concentrate on two. But just before we do that, just to observe another consequence. So this is something I mentioned, I stated in the previous lecture. Every computable NSP type sigma is denotable by a program in PCF plus bival. That's because if it's a computable NSP, we can write some, it's Turing computable, so we can write some P of this type that represents it, and then applying, and then I sigma of P will be an example of a term. This is in PCF plus bival. Yeah, so we're allowing PCF plus bival to write these interpreters. I sigma of P will be a PCF plus bival term whose NSP is P itself. So that gives us the completeness that everything computable is denotable. We can just read that off from this statement here once we've achieved that. Okay, so we're already seeing some applications that will flow from this. So how do we write our I sigma, which is supposed to turn an NSP represented by a type 1 object into a live thing of type sigma? Okay, so if we've got, let's supposing sigma is this type here, and we've got an NSP P, which is a bunch of lambdas, an expression E, and we've got our capital P representing P. Notice what we want to do is when I sigma wants to be a function lambda, a bunch of z's, and then we want to compute the value of this NSP expression E in the environment where we interpret each variable xi as the zi that we've been given. So remember, xi is just a bit of syntax. It's just a Gödel number for a variable. But we somehow want to think in terms of an environment where we're associating each of those with a live object of the relevant type. And so this means that anytime we see an application of one of these xi's within P to something else, we want to apply zi to the interpretations of these qi's. Okay, now you might already be thinking of some challenges here or some issues with this. So I've said we want to apply zi to the interpretations of these procedures Q. So what types will these Q's have? Well, they'll have lower types than sigma itself. So does this mean that we'll want to define this interpreter in conjunction with interpreters for these other types that might feature as the types of these Q's? Well, yes, it does. So we're going to be talking about some big mutual recursion here, where we define a lot of interpreters together. And that's one issue. And then the other issue is that as we descend in the syntax tree for P, every time we go under a lambda, the set of variables we have in scope will increase. So the number of variables that we're in scope, it's not just as if we can sort of stick with this environment here that assigns these zi's to the original xi's. As we go down the tree, we'll go under more lambdas, more variables will come into scope. So our environments will need to be able to cater for unlimited numbers of variables and the live values they're associated with. Okay, so these are challenges. So what's the saving observation here is that if we start with a procedure P of type sigma, and we look at the possible types of procedures Q that can occur within sigma, there are actually only finitely many types that they can have, and that finite list of types will be determined by sigma itself. I'll show you an example in just a second. In conjunction with that, there are only finitely many types that any variables could have. Once we've got a variable, supposing we've got a variable y that's found within NSP, we can apply y to things many times with it, in fact, infinitely often down a branch. So we can have, yeah, the number of variables can increase without limit, but the set of types they can have is a finite, statically determined set. So, for example, supposing we say our procedure P has this complicated type, but I won't read it. Okay, so let's say what types can procedures have within P? Well, in counting P as a procedure within itself, that means sigma is certainly allowed. And then what will the form of P be? It will be lambda and x of this type, and then an expression. So we'll certainly allow variables of this type. Okay, so this is a possible type of variables. And this x can get applied to, in the course of the tree, to various queues. And what types can the queues have? Well, the queue could have this type, or it could have this type. So we see that. Right. Sorry, we're saying. Sorry. Okay, a variable x will have this type. It's applied to a procedure q, which will have this type. So this type here gets to go in a set of possible types for procedures. And now this type q, this will have the form lambda y z something, where y is of this type, z is of this type. So that means that these two types get to feature in our list of possible types of variables. And then, because we can have a variable of this type, we'll be feeding that procedures of type n. So notice that n is a possible type for both procedures and variables, but for different reasons. Okay, it's a type of 1 because of this n here, and the other because of this n here. So you can see that by starting with the type signal we're interested in and descending, sort of looking alternately at this sort of odd and even constituent levels within that, so to speak, we can see what the total list of procedures of types that we need to cater for is. Okay, so these ideas suggest we've got these two issues. So we've got finitely many procedure types that we want to cater for. So we should try and construct by simultaneous recursion interpreters for procedures of each of these types. And these will be for procedures, but let's do that in conjunction with an evaluator for ground type expressions, and expressions within them can contain applications. And this will be something ground type as well. So let's construct all of these M interpreters here and these two evaluators by simultaneous mutual recursion. And all this is going to be done relative to environments which tell us the objects we've assigned to the meanings we've currently assigned to the variables that are currently in scopes. So now we're saying the variables, we've only got finitely many types of those. Okay, so again, the observation here is that because there are only finitely many possible types, we can take some type that's big enough that all of these types can be embedded within it. In fact, the type sigma itself would be plenty big enough for this purpose. So we can yeah. So yeah, what we're saying here is there's actually, for any of these types, it's possible to have, you can write a coding term and a decoding term, which, as it were, embed this type rho I in sigma, so that when you code and then decode, you retrieve the thing of type rho I that you started with. So what that means is we can use sigma to represent any of the values we're assigning the variables to in the course of this computation. And if we want infinitely many of them, that's okay. We could take, for example, n arrow sigma as our type of environments. So this n here we can use for, we feed as this function the Gödel number code for a variable, and this returns the thing we're currently assigned to. So we can get by the problem of seemingly infinitely many variables, infinitely many procedure terms by noticing that the types of everything are bounded. So hopefully by now you're already getting the intuition that how this works. So I'm afraid the next slide is horrible, but just in case you want to see, I'll show you some pseudocode for what these mutual recursions look like. So let's suppose our Gödel numbers for variables are informative enough that they actually contain the type information for sanity. And let's write these curved brackets x for the lookup of the value associated with x in the environment. This is to be used with caution because think of this as not just e applied to x, but the decoding of that. So think of this as the thing of the relevant type that's encoded in e. So the type of this, we're only allowed to write this in context where we statically know what type it's going to have. And likewise, we've got this extending an environment with a new binding assigning to code or x an object of the relevant type. And okay, we've talked about the fact that terms of type NRON can represent NSPs. So for pattern matching purposes, I'll write this double ceiling of P to stand for any term that's a representation of the NSP P, just to make the look a bit more readable than it otherwise be. So we've got these interpreters for these types. So we've got a bit of code like this for each of the types tau I in our list of possible types for procedure subterms. Okay, so an interpreter with respect to environment E of this term takes these arguments Z and it evaluates the body of this procedure expression, NSP expression E, with respect to this extended environment with these new bindings here. So the actual code you write here will be dependent on will involve the specific coding functions you've used for the types in question. But we know what those are because we're only writing because we know what tau I is. We're only writing. We write a separate bit of code to cater for each tau I. So it's all fine. And then our evaluator does this. Evaluating an n just gives n, not surprisingly. What do we want to do to evaluate a case expression? Well, we want to evaluate the application A, that's done here, and then we want to feed that to a function which takes an arbitrary I to the value of EI. And that's what we've done here. But we're using a bivalve for this application because we want to ensure that this application here is only done once. Okay, the behavior that this NSP is prescribing is just that we evaluate A, and then we take the value of that, we feed that to this function here. So this is the place where bivalve gets used in the construction of the interpreter, and that gives us a strong property. Yeah.
Can you expand more on how double upper brackets of P is made such that you can case match on these functions?
Okay. To case match on these things. So, right. If I give you a type 1 function representing an NSP procedure or expression or whatever, you can tell which of these forms it is just by looking at the root node of that tree. So, like by evaluating it at 0, let's say 0 is the address of the root node. You can tell. You can tell, for instance, whether it's a numeral, whether it's an application here, what the head variable is, and then you could extract. And then in this case, okay, in this case, what you read is you tell from the root that there's this list of lambdas there, and then the subtree of that. So from a term representing P, you can easily extract a term representing this E just as a subtree of it. So there's rather a lot of details compressed into here, but this is my attempt to balance readability with intelligibility. Okay. And then let's see how we interpret applications. So we've got an application term here. Okay. Now this X is just a bit of, again, by looking at the root node of this tree, we get X as a type, as just an untyped Gödel number. So we can case branch on the type of X. Yeah. And for each possible type of X, we write a separate bit of code that interprets the application. So we interpret the QIs using the interpreters of the relevant type. We extract from our environment E the value currently associated to X. It could be of the appropriate type. And now you see we're recursing back to this type. And then, as a final thing, at top level, to construct our interpreter for a closed procedure term P, we just use the interpreter at type sigma, starting with the empty environment. So that's probably as far as I want to go in that. I hope that's something of the idea. Okay, so I think the existence of these things is sort of an interesting computability theoretic fact in itself. But we've already seen a couple of applications, and perhaps surprisingly, we'll see another use later for the existence of these interpreters. How am I doing for time? Oh my word. Okay. I'm sorry. I think what I'll do, I will very quickly skate over this and get time. There are other interesting things you can do in PCF. If you want to ask me questions about those at the end, then do. I'll just a few more seconds. Okay. Right. So let's go to our final thing, which is this idea which relative observational equivalence. So recall that if you've got a programming language L with a reduction semantics and a notion of what you can observe, we say two terms are observation equivalent if in all term contexts C of L, we have that C of P evaluates to a given observable value if and only if C of Q does. Now, a lot of work has been in the semantics community has gone into trying to characterize observation equivalence for various languages. But what I want to point out here is that if you've got a language L that's a sub-language of a bigger language, L prime, it can happen that both the observation equivalence relations of L and L prime are hard to characterize, but the relative observation equivalence is fairly simple. So what I mean here is we look at observation equivalence for terms in the smaller language, but just with respect to context in the larger languages. It can happen that this is something we can get a handle on, and we can and is tractable mathematically, even in cases where the two individual observation equivalences are not. So a possible motivation for this is, supposing we're waiting to program in a big language that has sort of maybe some non-functional features in it, but we prefer, where possible, to write most of our programs in some well-behaved fragment, say a functional fragment. Okay, so we're keen on being able to reason about functional programs as they sit within this larger language, but we're aware that the programs we might be run in interaction with programs with other non-functional features. So you might be interested in can we characterize L observational equivalence, observational equivalence for L programs with respect to contexts in L prime. And what's even better, if many different extensions L prime of the same full language L all yield the same relative observation equivalence on L terms, that might mean you think this observation equivalence is really worth studying. We don't have to study a different observation equivalence for every L prime we consider. So just as a, right, okay. I'm going to, so this does happen. So take L to be PCF, for example. So we know from Ralph Loder's result that in a technical sense, observational equivalence for PCF is hard to characterize as an undecidability result, even for finite returns. Now let's extend PCF by adding local ground type state. And that leads to the language known as idealized algol. So it's known that in general, the observational equivalence for idealized algol is also quite hard as an undecidability result that shows that. It's not that I think that, you know, deciding things that fourth order functions are the be all and end all of anything. It's just that this is manifesting that there's some kind of complexity there in the structure. But supposing we consider the IA observation equivalence just for PCF terms, this is much easier. In fact, it's just something you can read off from NSPs fairly easily. So if you take you take NSPs, do a bit of pruning on them, and then you ask whether you've got the same thing. That's that gives you what you want. And this is, in contrast to the other things, decidable for finite PCF terms. So, for example, in idealized algol, we can distinguish. We've got two programs that do the zero tests on n, and we can we can't observationally distinguish these in pure PCF, but we can in idealized algol, as we can just pass this an argument which has a little counter cell which increments itself every time that argument is evaluated. Yeah, and return. Yes, this is a plus increment and return original value. So yeah, we get the value 1 from it this time. We can distinguish these, but on the other hand, we can't in idealized algol distinguish this term from this one. And this is because if you look at this subterm here, once you try to evaluate this subterm, there's no way it can actually give a value. It only places it leads up to the bottom. So it's sort of yeah, there's no hope of this giving you anything defined. So the idea is if you prune off these incomputable, so here we've got a little, if you look at the NSPs, the NSP corresponding to this bit of term will be this. And the idea is that we can just, because there's no path in that leads to anything non-bottom, we can just prune that. Okay. I want to get to my punchline. And now let's go a bit further. We've got to idealize algol, and let's just extend that a bit further by adding a single error value to the language. This is an error value which once the error is raised, that's game over. You know, it's just observed at top level. You can't recover from it. Let's see it. So it's maybe not so much known about in game semantics world, but the impression from my colleagues is that probably this observation equivalence is still quite hard. But now the observation equivalence for PCF terms within this language is easy. And in the sense that it is just equality of NSPs. And this is equational theory, I will, in the next few slides, write as curly n. So equality of NSPs with no pruning. So if we now look at the example of these terms that were observation equivalent before in idealized algol, okay, now they're not observationally equivalent because we can get this n to raise an error second time. You know, if we get this far, so this yeah, this thing we're passing in as our n. The first time it's called, it will return 3. Second time it's called, it's evaluated, it will return an error. So if we get this far, we'll see an error, which is different from going undefined. So we've got this observational distinction there. And what's more, once we've got this much observational power in our language, we find that this curly n arises as the relative observational equivalence for PCF programs for many other languages L prime that extend PCF. So here's an impressionistic picture of part of the programming language landscape. Let's get through this slide. I'll be quite pleased. So think of this as part of the space of programming languages. So we start with PCF here, which has perhaps a relatively generous notion of observational equivalence. We move up to idealize algol. We can make a few more observational distinctions. We add the error value. We can make even more observational distinctions. And now our theory is NSP quality. So the point is, from here, there's an awful lot of further stuff that you can then add without changing the observational equivalence on PCF terms. So all this world of sort of interesting language features, coroutines, vectanders, things like that. So we've got this quite sort of substantial, I would say, region of programming language space where, in all cases, the relative observational equivalence for PCF programs is just this NSP equality. Of course, you can add crazy things that will break that. Suppose you have a Lisp-style quote. So Lisp-style quote basically turns any term into its syntax tree, and that makes a mockery of the whole idea of observational equivalence, right? Because you can observe there's observational equivalence is just identity on terms. Likewise, if you have time-sensitive features, how many milliseconds does it take to something, that'll be outside here. Anything that's sensitive to the amount of memory you use, or goodness knows. So there's a sort of part of the world we might like to regard as civilized, and a part of the world that theoreticians like myself wouldn't want to touch with a barge pole. So what we can do is we can propose a criterion for distinguishing this civilized part of the world from this wild part. So we can propose conditions that will be satisfied in practice by all these sorts of languages, and we can actually prove a theorem saying that for all languages satisfying those conditions, this observational equivalence contains the theory N, the NSP theory. It might be larger than that if your language is smaller. So that's the sales pitch for this. So let's just see how far I get. Yeah. So let's actually take PCF plus bival as our core language, and in terms of, and we'll suppose we've just got an adequate translation of that into some bigger some language we think of as bigger. Okay, and let's write m approx. That's symmetric. Yeah, m prime. If the translations of m and n prime are equivalent with respect to observations in the bigger language, and we want to know when does this relation contain our theory S. So let's just look at examples of how this might work. So for example, if the bigger language is idealized algol, then to do this translation, we notice that we can translate bival into algol like this. So we've given an f and an x. We give ourselves a little local variable. We evaluate the result of x, store that in A, and then every time, and then what we pass to A is something which, what passed to F is just something which looks in A each time. And this will actually have the desired effect of evaluating X just once and caching the result. We can also more trivially take our bigger language to be actually PCF and translate bival by this. And this is one of the terms the kind that Phil was talking about last time, something which within PCF itself is indistinguishable from bival, but would be distinguishable in a larger language. So this is just saying that this slightly trivial case is covered by our theorem, but we're more interested in this kind of situation. Okay. Right, so we want to look what are some sort of sanity conditions on languages that mean that will imply that the observational equivalence is at no finer grained than NSP equality. So for functions n to n, let's write m twiddle m prime if they represent the same partial function on the natural numbers. In other words, m of a numeral evaluates to m if and only if n prime of the same numeral evaluates to the same m. Those m's should have hats on them. Yes. Okay. Okay. And recall that if m and m prime represent the same type 1 function in this way, then their bivals will have the same NSPs, because their bival will just be case n of I goes to whatever the value of that function I is. So it follows easily from what we've said before that this theory, curly m's, NSP equality, will equate everything of this kind when we've got different representatives of the same type 1 function. So if we're hoping that our observation equivalence contains n, a necessary equivalent condition for that will be that bival acts as a kind of normalizer for type 1 functions, in the sense that you can start with two type 1 functions that represent the same, two type 1 programs that represent the same type 1 function, although they need not be observationally equivalent. In bigger language, they might do different numbers of evaluations, their argument or something like that. But when you apply bival, that flattens out any differences between them, so that all you get is, so that any implementations of the same mathematical type 1 function will be observationally equivalent. So this, I claim, is one part of what it means to be civilized. And I think that if you reflect on civilized programming languages, you know about whatever, you'll hopefully agree that this is going to be fixed. If you're calling a function by value, and you're passing a value n to it, there really is nothing you can observe. There's not, no way it can interact with the rest of the world until it gets back to you with its results. So this is a key condition. And then I'm just about to wrap up. Our strategy for proving our result is to use interpreters. So okay. If we can show, so remember that the job an interpreter did was this. If P represents M, then the interpreter applied to P is NSP equivalent to M. So if we can just give enough conditions to ensure that the our interpreter applied to a suitable representative of the NSP for M, the bival snipped in here, if this is equivalent to M, then it follows by this easy argument here, down here, which we won't talk through, that if two terms have the same NSP, then there will be observation equivalence in this sense. And I will just show you what the conditions are. These are conditions which actually they're necessary and sufficient for our relative observational equivalence relation to contain NSP quality. So the hope is that for a given language that you're interested in, verifying these conditions might not be too painful by your favorite operational or delimitation techniques, although I've not really substantiated that claim yet. Okay. Okay, again, sorry that's rushed at the end, but that was the last part of my formal slide. So thanks ever so much for coming, listening, asking questions. Thanks to OHAB for making these lectures happen. I just say, for those of you who I don't know so well or didn't know so well beforehand, hopefully it's given you a chance to see the kinds of stuff I'm interested in. So anytime now or in the future, you feel you'd like to come and chat about this kind of stuff, now that you know the kind of stuff you can chat to me about, don't hesitate to get in touch. So
So once you know a programming language is civil, what cool things can you do with that fact now that you know that the observational equivalence includes the equational theory of NSPs?
what can you do when you know? Well, I mean, the hope is that that's just that's useful for proving things about programs. If it's an indication that it may be worth some effort, investing some effort in understanding this theory of NSP equality. As I've hinted at the end of this slide there, I think that these considerations are likely to form the basis of some sort of reasonable proof system for proving these observational equivalences. It won't be complete, of course, but it'll be reasonable. So the idea is these languages will just fall within the ambit of something we understand, and so if I see actual applications, and it will be to reasoning about programs. That's right. Yeah. Okay. So supposing we quotient out by this model NSP zero is closed NSPs, we quotient that out by extensional quality. So we've got a type structure that really is a type structure of sequential functions you can compute in PCF. In fact, from what we now know, it's the functions. NSPs themselves don't need to be computable. This will contain non-computable stuff, but it's easy to read off from what we've said that these are the functions computable in what some people call oracle PCF. So PCF plus an oracle for every mathematical type 1 option function. So once you've added in the function that gives you the So in fact, if your G is, for example, the partial function for the NSP itself, then relative to that you can compute. So can we characterize what these functionals are? So at first order, so we're talking about functions of RR arguments on n bottom. There's an old answer due to Robin Milner. So we can say that as a function of this type, so the other point is now just look at the function, forget about what NSP might lie behind it. Can you tell from the function whether it's a sequential function in a sense? So Robin Milner said we can say a function is sequential in the sense of being in this model if either it's a constant function or there's some argument which we look at first. So there's some argument I, position argument, I is a position of an argument, such that f is, first of all, f is strict in the ith argument. So we do evaluate the ith argument. So if xi is bottom, then will be bottom. Yeah. And furthermore, and this is sort of an inductive definition of types, if the value of xi turns out to be an actual number a, then just by sort of specializing x with a as the value of the ith argument, we get a function of another type, which is in turn sequential. So this is an inductive definition of the class of sequential functions by induction on R here. So that's all right. And you know about NSP, it's not, you can sort of see that this is a mental picture of almost the construction of the NSP. It's not hard to see that given this condition, one can reconstruct an NSP from the function. Going up to second order types, it's more subtle, but there's this what's my rather puzzling characterization by Kurt Sieber, who showed that if we've got a function on first order types, so the tau are first order types, and suppose we already know what these sequential functions of these types are. Function of this type is present in our type structure if f is invariant under a class of logical relations called sequentiality relations. So it's quite hard to get one's head around this, but again, it's a purely semantic characterization of what the sequential functions are at type 2. And so at least in the finitary setting, where we replace our base type lifted natural numbers by the lifted natural numbers up to n, we have an effective present, using these characterizations or other ideas, we can get an effective description of what functionals are present in the type structure at all first and second order types. In other words, a complete listing of them. Computably in Sigma, we can get a complete listing of the functions. That's as good as it gets. If you try and go up to third order types, it's known that the structure isn't excessively extensible as outflows result. So things get wild from there above. The other thing I want to say is, if you look at this structure from the perspective of classical domain theory, it's really weird. It doesn't. Don't try and use classical domain theory on this structure. It's my advice. So there's a few weird things. One weird thing I quite like is that there's even a first order function of two arguments that's both effective in the sense that you can effectively enumerate the graph for this, and sequential, let's say in the Milner sense, but not effectively sequential. In other words, so let's go back. So here we're saying sequential means, there's an argument I that's strict in. Okay. So the point is, yes, there's an argument here that we're strict in, but whether so we start by evaluating X, and then whether we evaluate Y or not is something we can't decide. So after evaluating X, we will either be a constant function or the Y will be an argument restricting. But we can't tell which it is. So there is a sequential procedure for this, but not an effective one, even though the extension function itself is effective. So that kind of quite amuses me. It was an open problem for a while whether this structure SF, whether it consisted of CPOs or not. And Dag Normann showed his original example, with the type 3, but then he proved that to show that even at this second order type, there's an increasing chain in the pointwise order with no upper bound. So that's kind of weird. So the point is that there's an increasing chain here in this extensional world that's not, as it were, shadowed by any increasing chain in the intensional world. So at the level of sequential procedures, every element of the chain has a sequential procedure, but they don't nicely line up. And at this same type, to mention, there are chains that have so there are some chains that have no upper bounds. There are chains that have least upper bounds in the order on the list that aren't the pointwise least upper bounds. So the pointwise soup obviously is sort of missing from the model, but there's something else there that is the least upper bound. But these don't behave at all well because computable functions are not obliged to respect the limits of these chains. You can actually, if you try to take this as your notion of continuity, there will be functionals that are PCF definable functionals that are discontinuous with respect to such sequences. So, kind of moral from this is all of this might well encourage us to say, well, stuff that, let's just not bother about PCF observational equivalence. It's just too difficult. It's brittle. It will break as soon as you add something else to it. Let's content ourselves with concentrating on this NSP observational equality as this sort of right or a natural and robust and much more tractable notion to understand.
And going back to Jesse's left, the question Jesse asked, a lot of the things you were talking about that are unsupervised, obviously are really hard to reason about, and that seems like a useful intuition that we maybe can't hope to do very much.
Yes.
If we start making these bizarre observations, but
yes,
it's curious how, I guess it makes sense as well how when you had an impoverished notion of observation, it's also different.
Yeah, right.
I guess that makes some sense, but does that?
Yeah, so I sort of.
How does that pan out in practice, it's hard to decide observational equivalence for PCF, but is that a problem?
I mean, not for anything other than deciding. I mean,
Because normally you don't, I guess normally we don't necessarily expect observational equivalence to be decidable anyway. We have some particular examples. we
Yeah,
want to
and
do
I mean, you know, I mean, you could live with not, if you had an equivalence that wasn't quite observational equivalence, because it didn't equate parallel or detecting programs, you know, I mean,
You
we
probably
could live
don't,
with,
yeah.
yeah, that's probably not gonna come back to bite you, is it? So,
There maybe are there interesting examples where you do want that level of granularity? Like it might be something, I don't know, you might imagine a normalization procedure, or you could only get the efficient version of your program if you have a very.
I'm not aware of any. I mean, I think, you know, the full abstraction problem for PCF just for many years seemed like such a natural goal to pursue that people pursued it with a lot of energy and vigor. But you know, I mean, now we sort of know that we know in what sense you can, you know, we've got as far as we can get with that, and you know, got results saying you probably can't do better. So. But as far as I know, no one's used the abstract game models to prove some exotic observational equivalence that can't be proved by
And do you have a precise characterization of that shape?
Oh, no, this is just impressionistic. I don't even know. I was thinking I might actually ask you. I mean, effect handlers, they're in there. Maybe they should be a bit higher up, because I'm not sure if they're.
They probably generalize.
They generalize a lot of, they generalize coroutines. So I was a bit in doubt whether they generalized higher order exceptions. I was going to ask you. I think from the game semantics people, I think remember there's something especially tricky about higher order.
They certainly don't generalize higher order store.
Oh, right. Oh, okay.
Well, it depends which version, right?
Oh, okay. They don't, okay, there's stuff they don't, okay, that's.
Well, it depends on how you type them.
Right, okay. I mean, this is just, this is give you an impression. Yeah, there's a lot of interesting stuff here we could hope to give models for and hope to reason about. And there's this.
So this is kind of open. It's not, you don't have a precise characterization of which things are civilized.
Yeah, I mean, the characterization I have is the things that satisfy
this
my
problem. So we can
By definition.
well, we can prove that something is civilized.
Yeah, but I guess your point is that if you prove that your functional code is correct, your purely functional code
Yes.
is correct using n,
Yes.
then that would stay valid.
That's
in all
stable,
the
stable and robust.
Whereas observation equivalence is actually quite a fragile notion
Yes, exactly.
to work with. Right?
Exactly.
And something that relies on observation equivalence to be correct.
This is a
It's
bit
probably
related
quite
to, Dan Geeker and Nicholas Severakis have this sort of campaign against conceptual equivalence. So I think what I'm saying is a bit like that you can you want to look at all ways your program could interact with its environment, not just, I mean, I don't know, I can't remember what that, I may not be saying exactly the same thing, but it's something related that, you want to focus on this robust notion. So that's it. Yeah, I hope that's convincing. There may be some interest in this NSP. And I keep getting to say NSP equality is the same as equality of innocent strategies in the game semantics. So these NSPs are very close to being view functions, but innocent strategies.